I am back again to the calculus stories for the enthusiast, but this time I'm just doing a screen recording because it will be slightly longish because and as a result of which I'm not getting the media where you can see me speaking to you because sometimes the media suddenly stops and I do not know when this whole effort goes off. Again, you have to redo it. I'm just trying to minimize my effort, being an optimizer myself. So here we are talking about the derivative. Many of my subscribers or many of my viewers would be someone who has basic ideas of what is a derivative. Here we are talking about calculus from a more fresh angle, little historical angle, and little fun angle. This is no extremely serious discourse of calculus, but it is also some little serious discussion of calculus. It is not a rigorous textbook to do your classwork or homework or your course material. Neither it is a popular science book where some stories are told and no symbols are used, or hardly symbols are used from which you can't make a meaning. It's something in between. That's my attempt. So this is my first attempt to move away from completely technical writing to something technical yet more fun, not course wise writing. So derivative of a function from say r to r, a real function, that we are just talking about real functions, is defined as follows: that you take the change in the function values when you make a change h in x, that you add a number h, could be negative, could be positive, to h, and then you look at the change of the functional value at x plus h and the functional value at x. What is the change? That is f of x plus h minus fx. This change divided by h, this is called the differential quotient. That limit as h tends to 0. So you have to take the two limits, left limit and right limit. If that exists, both of them are equal, and then that is called the derivative of f at x and is given as f dash x. See, f dash x doesn't depend on h. Here x is fixed. It's called the derivative of f at x. So x is fixed here. H is varying. So I can bring the f dash x to this side, and a little manipulation will show that I can write this limit minus f dash x equal to 0 as the following. Because I can just multiply h with f dash x and just club the whole thing together, and I will have this. Mathematically, this means here h is going to 0 and this ratio is also going to 0. So when this h is going to 0, this ratio is going to 0, which means the numerator must be going towards 0 much faster than a denominator. When such a thing happens, then the numerator is called the small o of the denominator. That is, this whole thing is called the small o of h. So then f of x plus h is obviously fx plus f dash xh plus o of h. That is, this whole thing is equal to small o of h. So f of x plus h is naturally this thing, which you can understand. So o of h means this, a quantity which when divided by h, that ratio goes to 0 as h tends to 0, meaning that O of h is a quantity which vanishes much faster than h as h vanishes. Now this is something you know, this part you know from your high school days, but possibly this writing would be new to you. Even if you have learned your engineering from your engineering courses, you might not have seen this kind of writing. But this is a very interesting writing and help you to do a lot of things. For example, this can be actually taken as a definition of derivative, and this can actually intuitively lead you to make definitions of derivatives in higher dimensions. Okay, this is something what we have now got, this expression from what we already had known. So the derivative is actually a number which allows f of x plus h to be expressed in this form. That is, if when h is very small, I can approximate f of x plus h pretty well as through the straight line f of x plus f dash x into h. That will be the kind of an equation of a straight line. So when h is very small at any point x, f of x plus h can be expressed through its tangent values. So that is basically when we magnify and move look at the area very near to a point x, it will look almost straight. That's the idea. So please, if h is quite far off from x, then this just taking f of x plus h to be fx plus f dash x plus h is a bad idea. So O of h is actually telling you the error that you occur as you move away and away from x in whichever direction you are going. And it also tells you that as you come near x, that is when h drops towards 0, your error decreases very rapidly, much faster than you can come towards x. Now the story of derivatives, the way we do derivatives today, derivatives for first principles are taught in high school, they are taught in whatever, taught in even colleges first year, whatever. But that had come much later. And let us see how the original geniuses like Newton and Leibniz and later on Euler and all these people have thought about handling derivatives. And many of you might not even have heard the word called infinitesimal. This infinitesimal is a very interesting word. Initially, calculus was called the infinitesimal calculus. That is, doing calculations with very minute quantities. What kind of a minute quantity? A positive quantity which can be made as small as one wants, but that quantity is not zero. Of course, Euler didn't like that this kind of definition, and he said that, oh, this is nothing but zero. But Leibniz or even Newton, they were contemporaries, were much earlier than Euler, of an earlier generation. So Leibniz, undaunted, made use of it. Sometimes you cannot always rely on rigor. Too much rigor might cause, as Sanjay Mahajan says, rigor mortis. We will talk about Sanjay Mahajan's work later. A professor in the US. So too much rigor will cause rigor mortis. So what people in those days understood, that let me see what I can do in an undaunted fashion. It's like there's a great saying which is often attributed to Feynman in physics, just shut up and calculate. So it's like that, just shut up and calculate. So I want to find the derivative of a function y equal to x square. You might laugh, oh, we know it's 2x, why waste our time? That is what I want to tell you. By trying to find the derivative of y equal to x square in the way which Leibniz has done is not a waste of time. It actually tells you what the masters thought. And to really get the feel of the subject, you have to always go to the masters. So when you had x plus, so what is the change in the value of y, the change in the functional value? It is f of x plus del x, the change in x, minus f of x, which is y. So delta y is f of x plus del x minus f of x is y. So y plus delta y is f of x plus del x. In this case, fx is x square, y is x square. So it is x plus del x square. Basically, what do you mean? Delta y is nothing but y plus delta y minus 1. So y plus delta y is just this. Now I square it up, just like a plus, this is just a plus b whole square. So x square plus 2x delta x into delta x square. Leibniz did a kind of thinking which physicists still do till date. That when they are looking at very minute changes. Only the changes of first order make sense. Changes of second order and higher doesn't make sense. For example, if you take a number between 0 and 1, the square of that number is smaller than the original number, the cube is further smaller than the square, and so forth. So, the smaller the number you take, the squares and cubes and to the power 4 and 5 and all become so small, they gradually become negligible as you make the original number smaller and smaller. So when delta x is very, very small, you just forget it. You just forget what. So what Leibniz said is that forget this delta x whole square. It doesn't do any good to you. It's just too small to be considered for any practical purposes. So let the game be continued. So what is x square here? X square is same as y. So y and y will cancel. Y is equal to x square, it will cancel. So what we will have? We will have delta y equal to 2x delta x. So Leibniz declared that the derivative is 2x. So but you say, okay, no, this is not what we have learned. This is not the thing when we learn about velocity in physics, we don't learn derivatives in this way. And you might think that, okay, this is kind of hand waving. During those days, this was not hand waving, this was a pretty decent approach, pretty decent argument. Actually, Leibniz later on started to write del y as dy and del x as dx. So this limit idea was thrown off. The limit idea was already used very cleverly when you are throwing off this grad x squares and grad x cube and all those things. So del x square. So when you had thrown off this, some kind of a limit idea had been already applied, which is hidden. So for Leibniz, this was a very fantastic way to do the thing. So this was pretty okay. But do we really need to throw off that higher order term? Let us see. And we will see that we really need not do so. Let us make sense of this infinitesimal idea. So from the previous discussion, what we could have, if I go by this expression, so this was y, so y and y would cancel. So I'll divide delta y by delta x. So I'll have a delta x cancelled out of here, but a delta x would come here. So what would happen? I'll have delta y by delta x is equal to 2x plus delta x square by delta x. So delta x square by delta x square, delta x dividing delta x square would give me delta x. Now as I take the limit as delta x tends to 0, this is exactly what is called the derivative. Even physicists learned the derivative exactly in this form, or or mathematician, that change of y divided by change of x, and look at the limit as change of x goes to 0. That would give me 2 of x here, because here as delta x will cancel delta x square and will give me delta x. So delta y by delta x will be 2x plus delta x. So as delta x tends to 0, this part will anyway go to 0. So in our modern term, we will also get 2x as the derivative. So this limiting process that we have done here was actually taken off in a very implicit way when you are throwing off this delta x square, when Leibniz threw off this delta x square. Any quantity, so delta x square is a quantity which vanishes faster than x. If you look at the graph of y equal to x, and if you look at the graph of y equal to x square, so when x is strictly greater than 1, the graph of x square lies above y equal to x, the straight line, which is passing through the origin and is at angle 45 degree to the x-axis. But when you come below 1, when the value of x is below 1, the value of the graph of delta x is above delta x square. So delta x square is coming to 0 faster than delta x, and that is why delta x square is a small o of delta x quantity, the one we had discussed it. So this is sometimes called the instantaneous rate of change. If t x was the time and y was talking about the distance, this is nothing but the velocity. Because once Lord Kelvin was teaching calculus to physics students, and somebody was telling that about his difficulty in talking about this idea of derivative. So he went in and said that this is nothing but the velocity. You see this is sometimes called the instantaneous rate of change. Rate of change at that exact moment. As time, if t the x is time, then we are looking at the change of the distance exactly at this moment. It is very difficult to make out. Basically, you are telling that when there is almost no change of time at that exact time, there is no change of time, there is no change of any movement. What is the velocity? But when Indians were very good astronomers, were observed the movement of the stars in early Common Era or AD, movement of the stars across, movement of heavenly bodies across the celestial sphere, they understood that at every moment, at every instant, it was moving. So it had some instantaneous velocity, which was called Tatkalika Gati in Sanskrit, and that there is a velocity. It is not that at time delta t, when delta t is very small, almost at that exact point it is holding back, it is stopping somehow. No, it's moving. So how do you actually compute the motion or the velocity exactly at that point? That is done through this procedure. So this is called the instantaneous rate of change of a function. Rate of a change of a function at a given point. It looks very counterintuitive, but we have to understand that you might say exactly at a point x, why is the function changing? It's just a one value. No, it's not. That doesn't make sense when you talk about physical objects. So this idea of a derivative essentially came from the movement of physical objects. So when a car is moving at a given instant of time, it is really not stopping. It has some velocity. It will move off. That is, if you look at a time, just a little few seconds or few microseconds after that, it has moved a little bit. So unless it was already moving there, it wouldn't have possibly moving there. So it was already coming and moving or observing, and the whole thing is moving. But you want to know how fast it is moving at one point. One will say, okay, it's just fixed. But no, we are not looking at, when we are really talking about the velocity at exactly one point, we are essentially looking at how it has changed in a very small zone around that time point. And then we will know how fast it has been moving around during nearby that time. So the rate of change, how fast its velocity has changed. That is the rate of change of the velocity. How fast the distance, how much distance has been covered within a very small time. So when you look at the limiting situation, you are looking at the rate at which it was moving exactly at that point. So that is the way it is defined. That is the only way instantaneous velocity could be defined, because when you had people, as Indian astronomers had observed these heavenly bodies, these bodies were obviously moving at every instant. They were not stopping, right? So that is why this concept, though counterintuitive, is a very useful concept. It's the rate of change at a given point. Rate of change of a function at a x. It is not called the change of the function at x. At x, there is no change of function. At x, the value is fx. There is no change of function. It's called the rate of change. This word rate makes all the difference, and that is what you really have to keep in mind. So if you look at this expression again, y plus delta y is y plus 2x delta x plus O of delta x. Okay, because we are just writing back this expression, where instead of delta x square, we are writing O of delta x. So what we have got back, this is nothing but f of x plus h. if delta y, delta x is h, and y is nothing but fx. 2x is the derivative, so f dash x, delta x is h, and O of delta x is O of h with a. So we are back to the square one. So what Leibniz threw off as higher orders is what physicists do at a regular interval when they study physics, and that is what these type of tricks are taught to the physicists. But mathematicians can build in the rigor, and that is how the rigor is built. But look at Leibniz's insight. The calculus that we do today, like fundamental theorem, integral calculus, and all, were due to Leibniz, right? So Leibniz was a rival of Newton. So he essentially, instead of writing x and del x, he wrote the symbols del y and del x to infinitesimal. And they and later on they were called the differential of y and differential of x. And you can understand that instead of you write del x, you are writing dx, and you will have the same situation for Leibniz. X plus dx whole square is x square plus 2x dx plus dx whole square you would ignore because it is too small, just forget it. And hence you will get dy equal to 2x dx, and you will write dy dx equal to 2x dx. The modern symbol of the derivative as dy dx is due to Leibniz. So for Leibniz, the derivative was nothing but the ratio of the differentials. But is it? Because here also there is a kind of trick where delta x square is thrown off and dx square is thrown off, and you just have forgotten it, as if it didn't exist, kind of thing. So would you like to really think that really derivative is the ratio of differentials? You can say, okay, when we were at school or high school, we were told never think of the derivative as the ratio of dy by dx. It is always ddx of y. So ddx is the operator, the differential operator operating on the function y to give you something. But hey, Leibniz, one of the originator of calculus, says no, the derivative is the ratio of differentials. So in our modern standpoint, how do we look at it? Is it the ratio of differentials? That is the story that we are going to talk about. So differential is the modern view. This view I learned from a book called An Introduction to Calculus and Analysis, Volume 1 and Volume 2 by Richard Courant and Fritz John. So Richard Courant is a very famous mathematician, and in his honor, the Courant Institute of Mathematical Sciences has been established. Is there in New York University, where one of the leading mathematical minds of the world work, including a very famous Indian named SRS Varadhan, one of the greatest probabilists. Now, let us see the modern view. Now, what did Leibniz say? Leibniz said that this dy is nothing but f dash x into dx, but dx is actually delta x. So Leibniz was writing delta x as dx. He didn't bother about anything else. So we already know from our expression that is y plus del y, which is nothing but f of x plus del x, basically, is fx plus f dash x into del x plus o, small o of del x. This is what we know is the definition of the derivative. Now, by going into what Leibniz told us, dy, the differential of y, is nothing but f dash x into the differential of x, which is we call delta x. Leibniz wrote delta x as dx. But can he really do that? Okay. Let us, from our modern definition, we define the differential of y, not the delta y. There's a difference between delta y and the differential of y. So delta y is f dash x delta x plus O of delta x, because y is fx. So we define the differential of y is f dash x into delta x. This is the thing we call the differential of y. This is the modern definition. This is somehow trying to making a sense out of what Leibniz had said. So what is delta y? Because fx is equal to y, fx and y cancels. Delta y is d of y, the differential of y, plus O of delta x, the small o of delta x. So the change in y is the differential of y plus some error which is associated with the quantity delta x. Now this is true for any differentiable function, doesn't matter. It just doesn't matter. So suppose we write y is equal to x. Suppose we write y is equal to x. We take the particular function y is equal to fx equal to x. Then f dash x would be equal to 1. And hence we will have dy equal to dx is equal to f dash x, that is 1 into delta x. So we will just have dx is equal to delta x, voila. So we can actually write delta x as dx. Though what Leibniz said that way, let us write delta y as dy is not very rigorous, but we can definitely write in a rigorous fashion delta x is nothing but d of x. The differential of x is delta x. The differential of the independent variable is same as the change in that variable, but the differential of the dependent variable y is not same as the change of the variable. The difference that when you take the change in the variable y, it is always the differential of y plus some error. And so we can write dy, the differential of y, is f dash x into the differential of x. So Leibniz was right that a derivative can be viewed as a ratio of the differentials of y and x. Isn't that beautiful stuff? Now let us go and try to find the derivative of the sine function. This is slightly critical. So after this talk, those who hear it and those who are really interested in calculus, go back with your notebooks and from the very first principle, that is f dash x equal to limit of h tends to 0 f of x plus h minus fx by h as h tends to 0, try to find the derivative of sine x and see where you get stuck. You can obviously write in the comments where you have got stuck, because I will do something more on finding sine x from what is called nowadays the first principles from the definition. The sine x is a tricky function. Trigonometric functions, or trig functions as Americans would like to call them, they are tricky functions. So this approach is due to the great mathematicians and one of my heroes, Leonhard Euler. Laplace had once said about Euler, read Euler, he is the master of us all. To learn some good mathematics, you have to go to the masters. In this discussion that we are going to have about calculus, our chief aim is to discuss about limits, slightly about continuity, about derivatives, about integrals, and about infinite series, about infinite processes. This is what calculus is made about, limits and infinite processes. So limits would lead to these kind of things. So you would know calculus much better at the very outset if you know that derivatives and integrals are names given to special kind of limits. So now f of x is sine x. So what is f of x plus delta x? So Euler didn't bother about that. He kept on writing dx instead of delta x. So sine of x plus delta x, you know the very basic sine a plus b formula, that is sine a cos b plus cos a sine b. So sine a cos b plus cos a sine b. Sine x cos dx plus cos x sine dx. Euler knew a lot about infinite series. A lot of things was through his intuition and through his experimentation, and lot of things was understood by Euler by linking uh, rather the exponential function to the trigonometric functions. This was a key idea. How do you put in how do you link the exponential with the trigonometry? So uh, let us not get into the history now. So he was brave enough and he just used the infinite series of sin x and cos x. So sin x equal to x minus x cubed by 3 factorial plus x5 by 5 factorial. So there's a plus minus alternating and with odd powers and so on. And cos x is 1 minus x square by 2 factorial and so on. Means 1 is nothing but x to the power 0. So just have a look at this very carefully when you actually listen to this talk. So what is the key idea here? Dx is very little of x. So when you take a very little of x, some quantity, always ignore anything other than the first order quantity. The first order quantity here is x and everything else is of higher power. So ignore these guys. So sin x is almost x. We had done this earlier by looking at certain calculator explorations. And cos x is almost 1. So here we have the term cos dx which can be replaced by 1, and here you have the sin term sin dx which we can approximate by just dx. So you get sin of x plus dx is equal to sin x plus cos x dx. So d of y, so that is what Euler wrote, this should be actually delta of y. So d of y is basically this. So finally they are the same because they have thrown out the higher order terms. So d of y is sin of x plus dx and minus sin x, change in y. And that from this expression, the above expression, you have nothing but cos x dx. So dy by dx, hooray, in the Leibniz style, we write this is equal to cos x, and we know that derivative of sin x is cos x. This may not be the most rigorous way, but this is an elegant, a deep insight into the way one can play with infinitesimals. In fact, whole books have been written on infinitesimal and its history. I will tell you about some of these books, which you can have a look. One of my next talks would be about, in this series of calculus stories for the enthusiast, about which books you can follow if you want to know calculus much better. So let us stop with Euler's working today, and we will get into slightly more details about actually how to hang around with sin x. When you take a very natural approach to the first principles, you will come to a term where you have to again use the infinite series, but it can be actually avoided, which using a very tricky trigonometric identity, which even if you have learned calculus must have forgotten. So with this, let me call it a day, and hope you have enjoyed this this talk on derivatives, and hope you'd get back to me through the comments. Thank you very much, my viewers and would-be subscribers. Thank you.